Hi everyone. So in this video, we're going to review the different methods we have for finding the volumes of solids of revolution. So we learned previously about the disk and washer methods, and then more recently, we've been talking about the shell method. And so we're basically just going to review all those different methods as well as just some sort of ideas about when to know when to use which method. And so there was one other type of volumes we've been talking about, which was in the video where I think it was called volumes of solids with known cross sections. So those were solids that were not solids of revolution. So those were the ones where like the cross sections were squares or triangles or rectangles or some other shape. So I'm not going to be covering those in this video just because those are kind of their own topic. Whereas the solids of revolution, those are the ones that can really be their volumes can be calculated in all these different ways. Okay, so I just want to quickly remind you what the disk and washer methods look like. So the disk method, and the washer method are both really kind of the same idea. So both of them have to do with taking your shape and imagining that you're slicing it. And you're slicing it along the same axis where you revolved it around so that you get these circular cross sections. So the disk method you can use if the cross sections are basically circles. So if your cross sections are circles, then you can use the disk method, and the disk method says that the volume is equal to pi times an integral from a to b of r squared dx, or if you're integrating with respect to y, it will be an integral of r squared dy. Where what is this r? The r is just the radius of your circular cross section. So we'll talk a little bit later in this video about, actually like pretty soon, about how you know whether you're integrating with respect to x or y. So we'll get to that. But just to remind you, where does this formula come from? Because I think you'll be more likely to remember it if you know where it comes from. Why are we doing pi r squared in this one and then 2 pi r in the other one? Well, the pi r squared comes from the fact that we're adding up the areas of these cross sections. And why are we adding up their areas? Well, if you take the area and then you multiply it by a thickness, dx, that gives you the volume of each slice. And if you add up all of these slices, you get the overall volume. So the pi r squared part comes from the area of the circular cross section. The dx comes from that thickness. And then the integrand, or the integral, means that you're adding up a bunch of them between one starting point and another finishing point. So the next method I want to mention is now the washer method. So the washer method honestly is really kind of the same as the disk method. It's just that, so it's still, slicing your shape and slicing it again along the same axis where it's been revolved so that you get these circular cross sections. However, with the washer method, in this case, you use if the cross sections are not just circles, but like a circle with another circle cut out of it. So something that looks more like, big circle with then a little circle inside. And so what does the formula look for this one? Well, similarly, you're adding up the areas of these circles. The difference is that now you have, if you wanted to find the area of this kind of donut, this part here, how would you find that area? Well, you would need to do pi r squared with the big circle first. And so that you would want to measure what this bigger radius is in order to find the larger area. But then you also would need to know what the smaller radius is because you want to subtract that out. And so if you put those into your integral, you end up with pi times the integral from a to b of big R squared minus little r squared dx, or pi times the integral from a to b of big R squared minus little r squared dy. And so where does this big R minus little r squared come from? Well, if you were to kind of redistribute the pi, you would get pi big R squared, and that would be the area of the big circle, minus pi little r squared, and that would be the area of the little circle. And so altogether, when you subtract them, that gives you the area of this part. And then you multiply that by the thickness, and that gives you the volume. You add them all up, you get the total volume. Okay, so the last method, the one that we covered in the last couple of videos, is pretty different from the other ones because no longer are you slicing your shape along the axis where you revolved it. You're now kind of decomposing it into these nesting cylinders. And so with the shell method, you can actually use it regardless of whether your shape has a hole in the middle of it or not, right? So for disc and washers, you do have to figure out, does this thing have a hole in the middle of it or does it not? The shell method you can use in either case. And so how does the shell method look? Well, the shell method, you're doing now 2 pi times an integral from a to b of a radius times a height dx, or 2 pi times an integral from a to b of a radius times a height dy. And so in this case, where are all these different things coming from? Well, 2 pi times the radius times the height, that's going to give you the surface area of a cylinder because it's basically 2 pi r is the circumference, and then you multiply that by the height, and that gives you the surface area, the outside area of a cylinder. And then if you multiply that by dx, that adds in the thickness, and so you're adding up then all these volumes of these cylinders. Okay, so that's the review of the formulas. I now want to talk about basically how can you decide which one to use. And there's going to be a few different topics that kind of come up here. So how can you decide which method to use? And so when I say which method to use, I'm going to be kind of lumping together the disc and washer methods because, again, they really are like the same method, and it really just depends. If you're trying to decide discs or washers, it just depends on whether your shape has a hole in the middle or not. So I'm more talking about, how do you know whether you want to use discs or washers as kind of one option versus option 2 being shells. So, and why are we even talking about this? Well, in the future, like on a future quiz or test or something like that, I'm not going to necessarily tell you use the shell method to do this or use the washer method. I'm just going to give you a solid and you have to figure out which way to find its volume. Okay, so first thing I want to talk about is which variable you're integrating with respect to, because this is really going to kind of influence, in many cases, which method you're going to use. So let's say that you are revolving about the x-axis. So if you're revolving about the x-axis, let's say that you wanted to use the washer or disc method. So if using well, that means that you're going to be integrating with respect to x. And so, this is something that we've seen in a lot of examples, and I'll sketch a picture to maybe help you understand why it is in just a second. On the other hand, again, if your shape is obtained by revolving around the x-axis, if you're going to use shells, well, then you have to actually integrate with respect to y. So that's what we saw in the most recent videos. So basically, when you're using washers or discs, the variable you're integrating with respect to matches the axis you're revolving around, and then if you're using shells, it's the opposite. So why is this? Well, if you think about what we're looking at here, so I'm just going to draw kind of an example of a shape. So let's say we have a shape that looks like this, and we're revolving it again around the x-axis. So I chose this shape because this is one, and we'll see this later, that actually can be done using either method. So if you wanted to do this using washers or discs, well, it would be washers in this case, right? Because we have a hole in the middle of this shape. And so if you think about it, first of all, when you're slicing, if you kind of like make the hand motion of slicing, that's what I like to do. literally go like this. You can't see me, but I'm making a hand motion where I'm doing like gesturing, making different slices. And my hand is moving from left to right, not up and down. And so that's kind of one way to think about why you're integrating with respect to x. It's because you're adding up these slices, moving from left to right, not moving up and down. The other way to think about it is if you were to add in the thickness, because that's really where the dx or the dy comes from. The thickness of this slice is a horizontal thickness, right? You're like literally, if you were to measure it, you would be measuring it as a change in x, not as a change in y. So let me draw that same shape, but now we'll draw in what it would look like with a washer, or sorry, with a shell. So if you're doing the same shape with cylindrical shells, now here would be like what a sample shell would look like. So it would look like this. So now if you look at the thickness of this cylinder, if you were to actually measure the thickness of the cylinder, the thickness would be now a vertical thickness. And so you're integrating with respect to y. Okay, so other case is that if you're revolving about, or how did I phrase it up here? Yes, if revolving, sorry about that, about the y-axis. So if you're using discs or washers, that means that you're going to be integrating with respect to y. And on the other hand, if you're using shells, then you're going to integrate with respect to, oops, I combined those into one word, with respect to x. So again, let me just draw a quick picture kind of showing what this would look like. So, and let me just scooch, I always do this, I put things a little too close and then I run out of space. So I'm just going to move this down a little bit. So what would this look like again with that same kind of picture up there? Well, if we had, I'm going to take actually just that same shape, but this time I'm going to revolve it now around the y-axis. So if you were using discs or washers, in this case it would be washers, right? And again, if you imagine like where are you slicing, you're going from bottom to top, right? So you're moving your hand, if you're actually like gesturing, making the slices, you're moving your hand vertically. And so that's kind of one hint that you're integrating with respect to y. And the other one is that this thickness is a y thickness, right? It's delta y, not delta x. Whereas if you wanted to do that same kind of a shape and use cylindrical shells instead, well, here would be an example of a cylinder. And in this case, again, the thickness would be, so now if you're measuring the thickness of this cylinder, it would be a thickness in terms of x. And so you would end up with dx, and so you're integrating with respect to x. So why is this important? Well, basically, there's going to be some situations where either method will work, but sometimes this limitation of which variable you're integrating with respect to will actually kind of force you to use one method or the other. So let me kind of summarize that, and then we'll look at an example. So if your function, so when I say your function, I basically mean the curves that you're given as your kind of boundaries. So if your functions is or are difficult to solve for the other variable, so if they're given to you in terms of one variable and they're difficult to solve for the other variable, then basically that will kind of force you to use one method or the other. So if you're in that situation, this will, sorry, I keep getting confused. This will point you towards one method. So an example of this is one that we talked about actually in a previous video. So in a lot of the examples I'm going to show in this video are actually going to be ones that we've already done. And so the point in this video isn't going to be so much to go through the whole procedure of actually finding the volume. It's more going to be talking about how to set it up. So, so yeah, I would expect in this video not to see so many, like there might be some where we set up the integral, but we don't actually like finish off the complete problem, just because we've already spent a lot of time, actually evaluating these. And this video is more about the decision-making process of what method to use. Okay, so this is one, like I said, that we did, I think in, when did we do this one? Maybe 2 videos ago. And so if we're taking this shape and we're revolving it around the y-axis, we're going to end up with a shape that looks like this. And so in this case, let's say that you wanted to use disks. So if you wanted to use disks, this is what a sample disk would be. So if you were trying to use disks, you would have to integrate with respect to y, right? So if you wanted to use disks, you would need to integrate with respect to, WRT is an abbreviation for with respect to y. And so that means you would need to solve y is equal to 1 over 1 plus x squared. You would need to solve that for x, right, in order to get that as a function of y instead of a function of x. So if you tried to do that, so we have y is equal to 1 over 1 plus x squared. That would become y times 1 plus x squared is equal to 1. And so that's y plus yx squared is equal to 1. And so this just actually is not like the very nicest equation to solve for x, right? You could do it, but it's like, it's not the friendliest, right? And basically what would end up happening is the equation you would get would be kind of complicated. Like even if you do solve it all the way through, the equation you get would be probably more complicated than the one that you started with. So this is possible to solve for x, but I'll just say, but it's annoying. It's easier not to, right? Like there's some where it's really easy to go back and forth, right? If you have like y is equal to x squared, you can rewrite that as x is equal to square root of y. That's simple. But other equations are just not so simple to go back and forth. And so it's going to be more work for you to do that. And it's going to be easier to just use shells. So in this case, it is easier to use shells. And so I'm not going to go through that because we already did this. It's in 2 videos ago. But basically, all you need to know here is that why is it easier to use shells? Well, because if you're using shells, then you're integrating with respect to x. And so you already have your function in terms of x, so you don't really have to do that extra work of solving anything. Okay, so next thing I want to talk about is kind of a way that you can visualize the differences between solving or using the disk and washer method versus the shell method in situations where basically there's one kind of dimension of your shape that's easier to measure than the other. So second kind of criteria you can use to determine what method to use is look at what distance is easier to measure. And I know that's very vague. I'll show you exactly what I mean by that in a second. Okay, so what do I mean by easier to measure? So I'm going to sketch a couple of examples. So the first couple examples we're going to look at is if you are revolving about the y-axis. So I'm just going to sketch a couple of examples here. So one would be something that looks like this. So this is kind of like, let me make this a little neater. This is kind of like the very first example we did on the shell method video. And then I'll draw a second example that we'll talk about after. So this would be if we had one that was like this. Okay, so what do I mean by easier to measure? Well, let's say that you were trying to figure out what distance this was in red. That would not be easy to figure out, right? Because what's the issue? Well, if you were trying to figure out what this distance in red is, you would need to figure out what's the kind of upper and lower function to subtract them. But this is all one connected graph. So in order for you to figure out what this distance is, you would have to kind of separate this into two different functions and subtract them. And that's just not easy to do. And in some cases, it might not even be possible. So it's just this, like basically anytime you have a curve like this, it's not going to be easy to measure kind of in the middle of the curve. What is easy to measure here is this, right? This distance is easy to measure because it's just whatever your function is. So let's think about, now knowing that that's the distance that's easy to measure, let's think about what that shape would look like if you were to revolve it around the y-axis. So if you take this kind of slice that I just drew and revolve it around the y-axis, what do you end up with? You end up with a shell. So if this kind of vertical distance is the thing that's easy to measure, when you revolve that around the y-axis, which is what we're doing, then that points you to using shells. Let me make this other example a little bit bigger so I can kind of point to it better. So now let's say you have kind of a similar shape function, but now it's kind of oriented the other way. So again, it would be difficult for you to measure this, right? Like that would involve breaking this function into two pieces and subtracting them. What you could measure is this, right? This would be the easier thing to measure. Because again, it would just be determined by whatever this function is. In this case, this would be a function of of y, right? Because it's like a sideways facing shape. And so what do you get if you take that kind of slice that we just measured out and revolve it around the y-axis? Well, it ends up over here. And what shape do you have? You have a disk. So basically what we saw is that if you can kind of like demonstrate for yourself, what is it that I can measure here? And then just picture what happens when you take that slice or that kind of line that you're drawing and rotate it around. Do you get a shell or do you get a disk? And whichever answer you get, that is what method you should use. So similarly, now let's say that we're revolving about the x-axis. So I'm basically just going to draw kind of the same pictures here. So now we have, again, a shape like this. But let's say we're revolving around the x-axis. Well, this is the same shape as we had just above, right? We already decided you can really only measure it this way. You can't measure it in the sideways direction. So what happens if you take that dimension that we can measure and you rotate it around the x-axis? Well, you end up with a disk. And then if you have, similar to the other example above, if you now have a shape that's more like this one, well, what can you measure easily here? You can measure this direction, right? And so now if we're revolving again about the x-axis, what's going to happen when you take that thing that you can measure and rotate it about the x-axis? Well, now you're going to get a shell. So I just think this is kind of a nice way to visualize what's going on here. Like truly whatever it is that you can measure, that measurement, if you draw it, just picture what kind of a shape you get when you revolve it about the axis that you're using. And so let's look at a couple of examples of where this came up. So these again are examples that we already did. So I think this one was, 2 videos ago. So in this case, we have this region here, this kind of like top of a parabola. And so this is an example of one where it would be difficult to measure this way, right? Like you would have to separate this parabola into two functions, two like positive and negative square roots and subtract them. It just, it's too much work. versus it is easy to measure this distance, right? Because that distance is just given by this function. And so what happens if you take that kind of shape and rotate it around so this case we're revolving around the y-axis. So you would get something that looks like this. Let me make that a little shorter. And that would be a shell. So this one you would want to use the shell method, and you can go back and watch the older video if you want to see the details of how that looks. And maybe just to say one more thing about everything that we've been saying here, basically what's going on is that whatever that distance is that you can draw in as a line, if you're using the shell method, notice that that distance becomes the height. Whereas if you're using the disk or washer method, that distance you're measuring actually becomes a radius. So that's really like if you're trying to connect, to like the formulas, that's what's going on here. And I guess what it boils down to is that when you're using the washer or disk formula, the real kind of crux of the problem is to find the radius, right? That's the kind of the trickier part of the problem. Whereas for the shell method, the thing that is kind of the more interesting feature you're finding is the height. Okay, so another example that we did, I think, in the previous video was now we have, again, this kind of piece of a parabola, but now we're revolving it around the x-axis. And so again, in this case, it would be very annoying to try to figure out what this distance is. But you can figure out what this distance is, right? That would just be determined by our equation. And so if you take that little distance that we just measured out and revolve it around the x-axis, we get a shell. So for this one, you would again use the shell method. And the difference is that in the previous version, or in the previous example, you would use the shell method and you would be integrating with respect to x, right? Because it's the y-axis, you're integrating with respect to x, versus in this example, you're revolving around the x-axis, so you're going to be integrating with respect to y. Maybe I'll even just add that in. So use shell method with respect to x, and then this one would be the shell method with respect to y. And then I want to look at another example. So this is one that actually we can do both ways. And we're not going to actually fully integrate this out, but I want to at least write down kind of the setup. So let's start by, and actually I should probably copy this image and put it down here so that we can draw on it twice. Okay, so let's start by trying to do this one using the disk or washer method. So maybe actually let me rewind for a second. So why is it that we can use either method for this one? Well, let me go in and label these a little bit. So this bottom curve here, right, this is actually y is equal to x squared. And the top one is y is equal to square root of x. So why can we use either method? Well, we can measure this distance, right? Because how would you get this distance? You would just do square root of x minus x squared, right? And that would give you that distance. But you could also measure this distance without much of a problem, right? So why could you measure this distance without much of a problem? Well, you would just need to solve these to get them as functions of y, and then again, you would just subtract them. So the difference is that in the previous examples, we had kind of like a shape that it was all within one graph, right? And so that's why it would be difficult to figure out what this is. Whereas in this example, we have two different graphs. So you can just subtract them to figure out what that distance is. So let's start by setting this up with the shell method. I don't know what I said earlier I was going to do first, but let's start by doing the shell method. So I'm going to actually, in this case, draw our solid. So our solid is going to look like this. Sort of. Let me make that a little better. Okay, so let's say we wanted to use the shell method. So the shell method would happen if we were measuring like this, right? Because we're going to be now rotating it around the y-axis, and so we're going to end up with a shape like this. So if we wanted to use the shell method, that means we need to figure out what is the radius and what is the height. So the radius is just going to be x, because if you're rotating around the y-axis, basically whatever x value you're at is going to be exactly what the radius of the cylinder is, right? If you're at x is equal to 0.5, then the radius will be x is equal to 0.5. So the radius is equal to just x. And then what would the height be equal to? Well, the height would be determined by the top function minus the bottom function. So that's going to be square root of x minus x squared. And notice that everything's in terms of x, and that's because, again, you can go back to the first set of rules we talked about, right? Which was about if you're if you're using the shell method, whatever the axis you're revolving around, you're using the opposite variable in your integral. Okay, so what would the actual integral of this look like? Well, we would say the volume is equal to so we would have 2 pi on the outside. And then what would our bounds be? Well, we're looking at what is the smallest and largest radius that makes sense in this, or x value that makes sense in this. And the first one would be 0, and the second one would be 1. So we'd have the integral from 0 to 1 of x times the square root of x minus x squared. And I'm not going to go through and actually evaluate this, but this would be a pretty simple one to evaluate, because you would just rewrite square root of x as x to the 1/2, distribute, and then you would have stuff that is fairly straightforward to find the antiderivative of. So now let's say that you wanted to use the disc or washer method. So in this case, it's going to be washers. And why is it going to be washers? Well, because we have a hole in the middle. So this is now going to be doing the same shape using the washer method. Let me actually write it over here. So what information do we need when we're using the washer method? We need to know what the outer radius and the inner radius are. And the radius has kind of like a different meaning in this context than it does, sorry, struggling to draw this well. Slightly different meaning than it does in the context of the cylindrical shells. So let's draw a sample disc. So again, why is it that we can use a disc or washer? Well, because you can measure this distance, and if you were to revolve that around, you would get a washer, right? So you'd get a washer that looks like this. And so really, this is the distance that we're trying to find here. Oops. And so how do you find that distance? Well, that's exactly why you do the big R squared minus the little r squared, right? That's to give you essentially something related to that distance. Okay, so in this case, like we said, we need to figure out what the little r is and what the big R is, and then we can put those into our integral. So the little radius, so now we have to be careful because we're now going to be integrating with respect to y, right, instead of with respect to x. And so that means we want to rewrite these as not being functions of x, but as being functions of y. So the top function was originally written as y is equal to square root of x. And so we can rewrite that as x is equal to y squared. And then the bottom function was originally y is equal to x squared. And so we can rewrite that as x is equal to square root of y. And so the inner radius in this case is determined by the graph of y squared. And the outer radius is determined by the graph of square root of y. And then how do we find our bounds in this case? Well, this time the bounds need to be y values, right? And so coincidentally, they're going to end up being the same here. But in this case, it's because our smallest, you just want to think about what's the smallest value of y that it makes sense to plug into this. And the smallest one is 0. The biggest one is 1. And so this time we're going to get the volume is equal to pi times the integral from 0 to 1 of, so how does this one work? Now we have to do big R squared minus little r squared. And so that's going to be square root of y squared minus y squared squared. And I guess I should add some extra parentheses in here. There we go, dy. And then you could simplify that. And again, this would be a fairly straightforward one to integrate. And notice that the two integrals we set up look totally different, but you would actually get the same answer both ways, regardless of the fact that the integrals look different. So let me just quickly summarize. I forgot to write up here what it was that we're doing here. But basically we're seeing that in some cases, either method works. And so in these cases, it's really up to you, what you think is easier. So personally, I think in this example, the shell method was easier. And so why do I say that? Well, basically we didn't have to do any, solving, we didn't have to flip these equations around to get them as functions of y. We could just use them exactly as they were. So that's why I think the shell method's easier in this case. Okay, so one last thing I want to mention is that sometimes there are going to be situations where, maybe you can set up the integral, but either you can't evaluate it or the integral itself is difficult to evaluate. So third kind of consideration is that sometimes you can set up an integral for the volume using either method, but only one method, or maybe let me say it this way, one integral is easier to evaluate. Or maybe even there might even be situations where one of them is actually not even possible to evaluate. So the example I wanted to give of this one was this function, which was actually, I think this was on the worksheet with the previous video. So this asks you to find the volume of the solid obtained by revolving the region bounded by y is equal to cosine of x squared, y is equal to 0, x is equal to 0, and x is equal to square root of pi over 2. That's this value here. So let me just put that in here. About the y-axis. We're taking this region here, and revolving it around the y-axis. So we're going to end up with a shape that looks, let's see how well I can do this one. This one's a little tricky. Something like this. Okay, so let's again kind of talk about, let's set it up for both methods, and we'll see that one of them will give us an integral that we do have the tools to evaluate, and one of them is going to give us an integral that we don't, at least not yet, have the tools to integrate. Sorry, I'm just trying to copy this whole thing so I can put it down here as well. Okay, so let's say that we wanted to do this using the disk method. So if we tried to do this using the disk method, this would be our disk, and so that would mean that we would need to figure out what this distance here is, right? We would need to know what the radius is. So if we tried to use the disk method, we would, first of all, okay, so notice that we would need to be integrating with respect to y if we're using the disk method. And so that means that we would need to take this equation, y is equal to cosine of x squared, and we would need to solve it for x. And it turns out that this one, it's actually easier to solve for x than it looks like. It probably looks like it would be difficult to solve for x, but it's not that bad. So what we would need to do is take y is equal to cosine of x squared. So how do we get rid of the cosine? We could take inverse cosine of both sides. And it's not guaranteed that taking inverse cosine of both sides is going to give you the exact same part of the graph. But basically, because of the piece of the graph we're looking at, I don't want to get too deeply into this, but it has to do with the range of inverse cosine. So basically, when you're taking inverse cosine, it's only going to give you one certain part of the original cosine graph, and it happens to be that in this case, it kind of matches up to be the right part. So we would get inverse cosine of y is equal to x squared. And so that would tell us that x is equal to the square root of inverse cosine of y. Okay, so that would be our radius, right? So now we know that the radius would be equal to the square root of inverse cosine of y, because that's our graph, right? That's the curve that is determining that radius. Okay, so let's actually set up this integral. So this integral would now be the integral from 0 to 1, right? Because we're looking at the y values in this case, that would be included. And so it starts at 0, ends at 1. And then we would have the radius squared, and I forgot pi outside. And then we would do the radius squared. So that would be this thing squared. And so that's actually kind of good news that we're squaring it, right? Because that means that we're going to get rid of the square root. So we're going to get the pi times the integral from 0 to 1 of inverse cosine of y dy. So why is this an issue? You know, it looks like it's a fairly simple thing to integrate, but notice that, you know, we do not know the antiderivative of inverse cosine. We know the derivative of inverse cosine, but we don't know the antiderivative. And so this is one that you could look up, but it's kind of a complicated antiderivative. And you know, if this was, say, on like a quiz or a test where you're not allowed to use the internet, if you got to this point, you would be stuck. So this would not be the correct method for evaluating this integral. Even though we could set up the integral, even though we could solve it for, you know, the other variable and we could find the distance, it just gives us an integral that is not friendly. Versus if we go and use the shell method, so what would that look like? Well, now we would be taking a cylinder, so something like this, and so we need to figure out what the radius is. So the radius is just going to be equal to x in this case, because we're revolving around the y-axis. So every single x value is a possible radius, and the actual radius of the cylinder is the same as whatever x value you're at. And what would the height be? Well, the height would just be equal to the function. So that was cosine of x squared. So now we're going to write down using the shell method. So to write down the shell method, we would say the volume is 2 pi times the integral from, so what's the smallest x value that makes sense would be 0. And what's the largest one? That would be our largest radius, which is the square root of pi over 2. And so then we would multiply our radius, x, with our height, cosine of x squared. And so initially, you know, this might look like a complicated integral, but this is actually a pretty easy substitution. So I'm not going to go through it because this is on the worksheet that went with the, I think the first shells video. And so there's full solutions on that. But basically this we can solve. So this integral can be evaluated using substitution. So you would set u equal to x squared, and then that would give you du is equal to 2x dx, and so basically you would be able to get rid of that x. Okay, so that's pretty much it. The bottom line I would say is just, you know, and I know I've said this over and over again, but this just is really important in this class. You have to be comfortable with some experimentation in this class. There will be times where you try something and it doesn't work and you have to try a different method. That is just part of this class. So, you know, I know for a lot of students, maybe that makes you uncomfortable. You want to just know what's the formula? What do I do in this case? This is just really not a class that caters to that mentality. You know, you really are going to, in order to be successful in this class, be comfortable trying things. And so that might mean doing something like, you know, doing this one with the disk method and being like, oh, wait, I can't actually evaluate this. Let me try the other way. And the more you're comfortable with experimenting and trying things, the more you'll learn for yourself what works and what doesn't. So if you are following along on the homework, there are some problems on the homework that are meant to go with this video that they don't tell you what method to use, right? And so you can expect on those problems, on some of them to use shells and on other ones to use discs or washers. So, the first set of problems on the homework is all going to be shell method problems because those go with the shell method videos, but make sure you're paying attention. When you hit a certain point on the homework, you can expect to have some other method problems kind of mixed in. All right, I will see you on the next video.